So welcome everybody to the last lecture on statistical machine translation of this semester. And the lecture is going to be devoted to multimodal machine translation. So we're going to include speech and vision as additional aspects of the translation. This is the outline. I'll first give a very brief overview of including all this additional information, and then I'll focus on speech translation, which is essentially combining speech recognition with machine translation in order to be able to translate what people are saying instead of what has been written in the text. And there we'll talk about the immediate integration of these two independent systems, so if we just put them one after another, and we'll contrast that with recent approaches where the whole task of going from the source language speech to the target language text is being modeled in one step with some deep neural network. So that would be the end-to-end approaches. And in the second part of the lecture, I'll be talking about including visual information. There is a very recent survey on multimodal approaches to machine translation by Sulubachak and colleagues, and I heavily use that because it provides the most recent overview of the approaches, and it's a great resource. It also discusses, which I'm skipping actually in my talk, it also discusses the data that is available for all these enterprises, and obviously data is always critical because you have to have the right combination of inputs and expected outputs to be able to train these tasks. We'll mention some of the data issues later on, but if you want to look at direct links to corpora of images and the parallel text with images, parallel text with video, for example, or sound recordings, please go to that review. So this is what we have been doing so far. We have always had the text in the source language, and we were using machine translation to get to the text in the target language. And this time we're going to complicate it a bit. We're going to add the speech on the source side. So we need some technology to convert the speech into the text that the machine translation system is ready for. And the next step that people may want to do would be further to convert the text back into speech. So that would be a speech-to-speech translation. So you could have a system that sits in your ear as the babelfish, and whatever it hears, it will whisper it to your ear in the language that you speak. This would be a cascade of 3 independent components, and that cascade obviously brings some issues. Some information is lost at the boundaries of that cascade. So what people have been working on are direct attempts. One of these is often referred to as spoken language translation, and that goes from the speech in the source language to the text in the target language. So there is no explicit transcription used in the middle step. And if you want to go directly to the speech in the target language, this would be a speech-to-speech system. I'm not going to talk much about this, and actually I know nothing about text-to-speech, and I know very little about ASR. I'm only focusing on the machine translation aspect and contrasting that combination of ASR and MT with the spoken language translation. This is not everything that we could have. We can also have images. So this is an illustration. In this illustration, there is also some image which complements the source text. And this image can be used in image captioning. That would be automatically describing what is in the image with text in the source language. And that would be a monolingual task. But we can also use this image in some image-guided translation. So there the system would have access to the source text, some visual cue, and then it would be producing the target text with the help of the image. So this is what we are going to discuss in the second half of the lecture. And what we are not going to discuss, but what is still a very interesting emerging technology, is some visual guidance or video guidance to the translation. So if you have the speech, and the speech is present in the video, or if you have just a sequence of images, a video which is related to the text that you are translating, you may want to include this information in processing of the source text, again, to better choose the target words. So the visual guided translation is something which we will see being developed in the coming years. There are only first attempts so far, and I'm not going to discuss them today at all. Yeah. So let's look at the first part, the spoken language translation. So we already know machine translation pretty well. This is our 11th lecture on the topic, so you know almost everything. And the important thing that you have always known, but you have to realize it again, is that the input here are usually grammatically correct individual sentences. Sometimes we were working with the whole documents, but we were never working with like unclear snippets of text. These were sentences. Yeah. Then one particular aspect of machine translation which we have not discussed, and there are insufficient details on it in this lecture, but it's also getting fashionable or popular among the researchers, is something which is called incremental machine translation. So there are multiple reasons why you may want to process the input to machine translation incrementally. One of the clear motivations is that the input is still being uttered. So if you are talking about incremental machine translation, that means that it is text-based, so there is some text source, but the sentence is not fully complete as you are translating. You are receiving the words one by one, and you have to decide whether you want to wait for more words or whether you want to emit the current words. And it obviously depends on the language combination, on the source language and the target language, what is the best tactic to take. Depending on these languages, sometimes you have to wait for very long, for example, until the German verb comes at the end of the sentence. What interpreters do is a whole set of strategies. They maybe keep some of the output vague, and they leave all the backdoors open so that they can recover from the new information that will still come. The motivation for incremental machine translation as a research is to keep the machine translation output stable, because machine translation, the standard one that operates from sentences to sentences, is free to reorder the words in any way. And if you imagine a partial sentence and then a new word coming to that partial sentence, then suddenly this new word may hint the empty system, and it actually does hint the empty system, to reshuffle the sentence in a very crazy way. So if you have shown your partial output to the user, then suddenly the whole output may change, and that will be very annoying or distracting, so the user would not be able to follow this changing text too much. So the main aim of incremental machine translation is to provide the stability of the output. Then the spoken language translation, as I said, the input is the sound in one language and the output is sometimes text. Some people use this term to refer to speech-to-speech translation directly, but to make it clear, I'll talk always about speech-to-speech translation when there will be the target in voice already. And the benefits for the direct speech-to-speech translations is clear again. There is an option, there we aim at direct modeling. So we would really have a deep neural network model which processes the time frames in the source language and produces time frames in the target language. And thereby it will handle all the differences and commonalities between the languages. And we also have a direct access to features that are outside of the verbal domain. So we could preserve the voice, the tone, the prosodics, all these bits. It would be rather difficult to ship this information, or a little bit more complicated to ship this information along with a text-based translation to make the text choices in the target language good, and also then when synthesizing the target voice to reflect what was expressed in the source language. So first, let's look at the cascading machine spoken language translation. So we will be simply connecting together two components, the speech recognition and the machine translation. This is a motivation why it makes sense to put these two technologies together. This is the performance of speech recognition in the recent years after the introduction of deep neural networks, and through a series of developments, including more data or new algorithms, the systems got up to the human level performance in around 2017. So we can hope that the speech recognition will be better than humans. So the transcription of spoken language into words will contain fewer errors. This is the standard measure, word error rate, and that would be better than if a human was typing what has been said. We have discussed in the past, bear in mind the caveats on the evaluation, that machine translation is also getting on par with humans in some settings and in some evaluation ways. So if we plug these two components together, we really should get a great speech translation system. So the idea would be to run ASR on the sound that you want to translate, and then you would run the machine translation, and that would give you the superhuman interpretation of what has been said. Well, it's not that easy. The first problem is that the ASR systems are trained and evaluated and all that. They're focused on producing lowercase words. And machine translation has always been translating individual sentences. And as we will see, it is still not a very straightforward step to get from the sequence of words to correct clear sentences that should be translated. So that is something that you have to resolve. You have to segment the flow of words into sentences, and there could be some uncertainty. We'll see some examples of problems that arise from that. So if the ASR is not sure, for example, if I say ice cream, it could be the delicious cold thing that you eat in the summer, or I could be mentioning that I'm screaming because I got afraid of something. So this ice cream is an ambiguous sound, and the system, if it has to emit only one output, will guess what the correct output should be without access to further context, and then the machine translation will take that candidate, for example, the delicious summer thing, into as the ground truth, and it will translate it into the target language. If we had some n-best list in between these two components, if we were shipping uncertain outputs of the ASR, then obviously there will be lower risk of the user getting a completely confusing message. There is, if you want to deploy the system, there are further things, and I'll talk about them today. One problem is already at the very beginning of the pipeline. You have to acquire the sound, and then you have to present the output to the user. And that is again something which can have a very delicate interplay with the underlying algorithms, because you do not want to overload the user. You don't want to expose the user to all the possible candidates that you are considering. You want some stable and correct output as soon as possible. If you are deploying it really, and that's what we are doing in a European project called Eliter, you also need to put these components together to a working system, and this integration can be pretty hard and can introduce further errors, which I'm going to mention as well. So if you have independent systems, you will be acquiring the sound, you'll be shipping it to the ASR system, then the ASR system would recognize the lowercase words, you would ship it to the sentence segmenter that would do the sentence segmentation, then you would again ship it to maybe some other institute on the earth in Europe. It will translate individual these sentences into the target language, and there would be no room for any uncertainty, so no ambiguity of the input can be reasonably well handled there. You would have to be sending NBEST lists, for example, and then you ship it to some place where it gets presented, and then it is presented. And what we are trying to do is not only to put this pipeline together so that we can transcribe and translate some videos. We're going to do this live in real time. So we're trying to subtitle online sessions with in another language, and that online aspect makes it again difficult in a certain way. Here is a summary. During this lecture, I'll be going somewhat back and forth between the practical problems of the deployment and the theoretical considerations and the modals under the hood. Right now, I'll focus for a little while on the infrastructure. This is the architecture that we have in our project. And there is one central component which we call the mediator, and this mediator serves as a hub for all the different workers, and these workers are the independent systems developed at the participating universities and institutes. So there are people who work on the speech recognition, there are people who work on the segmentation of the flow of words into sentences. Many of us are working on machine translation engines. There is then the final presentation, and that presentation goes to the web where it is observed or watched by the participants. So if we want to subtitle a session, we will start a client of this, and the client will gather the sound, it will ship it to the mediator and ask for the complete processing pipeline, and the mediator will connect all the different institutes together, and it would ship the packets with sound data to the ASR, and then with the word candidates and so on, and finally it would receive a confirmation that the whole input has been processed, and this all happens like online with partial input, and these partial outputs are also propagated along the pipeline. So the web keeps constantly updating as there is the flow of new words coming in and as these words are translated. So the good thing is that these workers stay alive, they stay connected to the mediator. So when the pipeline crashes for some reason, then the client can be simply restarted, and the workers will be quickly reconnected. The modules do not start again. If some of the institutes has some hardware issues or network issues, it is very easy to deploy replicas in the system, and the mediator will again choose the workers that are serving well at the current point. So this architecture is resilient to some types of errors, but not to all types of errors. So I'll talk about the possible issues that we have. Actually, these are not possible issues; these are true issues that we have ran into in our test sessions. One of the issues was indeed that there was some internet connectivity problem at the ASR partner, and the whole pipeline was then slow, and we didn't know. So we have run like a pre-test session on the evening before that day, and everything worked smoothly. And when we were doing the live subtitling, suddenly there was a long delay, and we didn't know what is happening. And well, there was some reconstruction happening in the building of that institute. So that was an unexpected delay. And this architecture is well complex, and still we need to add proper diagnosis tools so that we would know if the whole output is the final output is delayed. We need to know where the delay is coming from, and it is pretty hard to diagnose to like debug this multi-party system, especially if it's this way non-deterministic. So one day it works and another day it doesn't work because there are too many components involved and they are distributed in the space. There is also a number of issues that you can have with the sound input. I'll mention some of these on the following slides, but essentially if the first cable is badly plugged in, then the sound quality is bad, and then nothing can recover from that. Then there is a final problem at the presentation. So maybe there is some delay between or communication bottleneck between the presentation worker and the web. So the users will see the delays, some unacceptable delay of the subtitles on their web browsers. And also, obviously, there is the end user devices that can themselves get like overflown with the data, overloaded, and they will not be presenting the subtitles live enough. So if you are trying to provide the complete pipeline, you are responsible in a way for both the acquisition and also the final presentation. And there, the user can actually spoil all your business with just an overloaded machine. We also had a strange misconfiguration issue, and it took us quite a while to diagnose it. This is a complex setup, and the error that we made was that we happened to start the ASR system locally. That was intentional because the models, we had the models compiled only on the particular machine, which was directly acquiring the sound. So that was on purpose. But what was not on purpose was to ship the sound twice, first to the mediator and then serve as a worker in this pipeline. This is a tiny typo in the configuration. The whole pipeline works, but it is delayed because your first mile connection is overloaded with the sound that you are shipping there and back. So again, this is something which is very easy to make as a mistake and quite difficult to realize. Let's talk about the sound acquisition now. Here is an illustration of what a colleague of mine did when he was presenting in one of our test sessions. He attached the chest mic to one of the close to his shoulders, so on the one side of his body, and then he was talking to the other side where the screen was. And this distance, like talking in the wrong direction, has decreased the sound volume and the clarity of the sound, so that the ASR was not working well. We made a very little comparison in one of the sessions. This is based just on 3 minutes, so this is something that we should really redo. But we have tried two types of mics. One was the chest mic, and one was the headset microphone, the one which is just very close to your mouth. And there is a clear benefit of using the headset microphone because the distance from the mouth doesn't change, so there is no need to adapt the volume for the system, and you set it up just once, and that works. So for our sessions where we really want the best performance, we always use the headset microphones. If people use handheld microphones, there are very common problems. People could cover the microphone with their hand. They could put it too close to their mouth. They could put it too far from their mouth or too far below their head. And they could also stand in front of the loudspeakers, in which case the microphone would be also receiving the same sound with a little delay. So maybe this would not be recognized by the audience, but this double sound wave could be already damaging the ASR quality, because obviously it is not trained on like sound combined with itself with a small delay. And then there is a very long sequence of the knobs on the pipeline. So when you are acquiring the sound, you really have to be sure that every intermediate component is producing output in a reasonable range of volumes. So if the output is too quiet, then you are not getting the signal. If the output is too loud, then the components further down the pipeline will fight against that, and they will clip it. So you're losing some of the frequencies, and then suddenly the ASR will not work either. So I've talked at the beginning of my lecture about the superhuman quality of speech recognition, and we tested this superhuman quality ourselves in one of the realistic setups. So here is an example of all the challenges that an ASR system would face. Let's say that the speaker was a high school student. We had those in one of our test sessions because we were taking part in a festival or fair trade of student companies, like mock business companies, and they were presenting their companies. So let's imagine that one of the students was trying to say, you have a bottle? Oh yes, we're situated in the heart of České Budějovice. So this is what he wanted to say. And unfortunately, his pronunciation, because he was not native English speaker, was wrong in the word bottle and also in the weir. So he would say, you have a bottle? Oh yes, we are situated in heart instead of hearth of České Budějovice. And there was additional background noise. So this is what was actually uttered and what appears in the recording then. Then if someone is present at that scene and he's listening to that, then he would probably understand you have a bottle. That would be unexpected. So only later on from the speech he would realize that this is a hotel on the river in a boat. And he would, the listener would be able to recover from the mispronunciation of heart and of weir, but he may not know České Budějovice, so that then he would know that some city name was mentioned, but he would not be able to recognize it. The current best systems that we had recognize just, oh yes, the off, because the noise was so bad that they simply couldn't catch up, couldn't recognize any words. If the noise would be somehow cancelled, or if the system would be resilient to that, then it would have recognized something like, you have somebody too instead of the bottle. Oh yes, we're situated in heart. Which can we do? So the České Budějovice is not in the vocabulary of the ASR system, and that would fail. If the ideal output, the thing that we were hoping for, and maybe a knowledgeable person would be able to understand, would be well, to recognize what the user wanted to say. You have a bottle, and then České Budějovice. So there is a number of problems, and all of them play against us. All of them play against us. So here is a summary from that student fairs festival. So if we look at the word error rates, on the very first slide I was talking about the word error rate of 4%. So 4% in 100 words are misrecognized, and that would be the human level of recognition quality. Here we are 10 times worse. So this is realistic recordings, difficult conditions, and for example, the Google ASR has a word error rate of close to 90%. So only one word in 10 is probably okay. The system by Edinburgh is also very high, and the system of the partner Karlsruhe Institute of Technology that we have in the project works best, but they still have the 40% word error rate, so 10 times worse than the humans. And this is the performance measured on the recordings. So this is actually offline, so the recognition after the recording has been made, not the online mode. The offline recording and evaluation where all the systems were able to produce any output whatsoever. And if the sound input is too bad, some of these systems really give up. So if we evaluate on all recordings and we give a score of 0, like a 100% word error rate, if the system has given up, then we will see that the scores are yet a bit worse. So the Google is giving up, and it is approaching to like total failure on that. It's close to 100% of word error rate. So nothing really recognized. Here is an example. I can play it for you. So the sound quality may be bad now in the live session, but we'll put that in properly. So here is.
We're going to. Hi, 22nd. Of course, I don't mind it. While you wear those high heels, if you would wear such sneakers, I know one really
So that was this part. The manual transcript said, why do you wear those high heels if you would wear some sneakers? I know one really good store that deals with the sale of free time footwear. And the Google recognition, so this is the best segment in that small collection. The best segment as recognized by Google is, why do you wear those instead of those high heels if you would wear some sneakers? I know, like no instead of that I do know, a good star instead of a store, and free down food instead of free time footwear. So you see many errors in the ASR output. And part of this is because of the poor sound acquisition, the noise in the background, but a serious part of that is the mispronunciation. That is a non-native speaker that we were listening to, and another part is the spontaneity of the speech. These were prepared sessions. The high school students have worked hard to like test these sessions because they were competing in their presentation capabilities, and yet obviously they made various grammatical errors, and the grammatical errors then combined with the pronunciation errors render the sequence of words difficult to properly recognized. So if the system cannot really trust the pronunciation and it cannot really trust the sequence of words because the grammar is wrong, then it is very likely to choose some wrong wordings. So the human level of performance would be 4 words in 10 to be wrong, and in our test set of these 90-second pitches, we were 10 times worse, and the online system, for example, by Google, was failing almost completely, and similarly Microsoft ASR as well. So you can read in many papers that the speech recognition is getting superhuman, and that's true in that particular setting of that experiment, but it is usually far from truth if you use some noisy input and you don't have a good control of the recording environment, and if your speaker is a non-native person. So that was like a reality check for the speech recognition, and now a reality check for machine translation. There again, we were talking about getting superhuman. Here is an example of a text input sentence, but it is much more difficult to ask if you do not have any clue. And the error that I'm demonstrating with our system into German is this mistranslation of the if. It is much more difficult to ask if you do not have a clue. So the if is translated op, as op, and that corresponds to the English whether. So the meaning that the German speaker gets is that it is difficult to ask whether you understand or do not understand. It's not that it's difficult to ask in the case when you don't understand. So this is the standard ambiguity of words and standard translation error, and these will appear in the outputs in addition to the errors induced by the speech recognition pipeline or the component beforehand. Then another example is some word which falls out of the vocabulary. You can be reported after some profanities. This was translated as you can be reported due to some professional things. So this profanities was not known to the English to Czech translation system, and the subword units played against the system, and it started the word prof, and it didn't know how to continue, so it made up something more frequent, professional things instead of profanities. Here is an illustration how the bad speech recognition and some errors in machine translation totally depart from the original meaning of the sentence. So if we are using just speech recognition system, then the words that are recognized are related, they are very similar to the words that were actually uttered. By the way, it's very interesting and funny to use a wrong language speech recognition on some speech. So when I was running Czech speech recognition on some English, I saw Czech words. They did not make any sense in Czech, but they were sounding. Their sound was very similar to the corresponding words in English. So if I read those words loud and then I listened to myself again, I could recover the original English words and thus the English meaning. So the errors in the ASR alone are recoverable by human users because you will think, what is a simpler word, what fits there? Unfortunately, in the cascaded approach, you take this single output as a string and you take it as the truth and you then ship it to the machine translation system. And the machine translation system will use totally different non-similar words anymore. So it will very much obscure the original meaning. So here is the example that what the system for speech recognition did. It produced the output, and the goal of my thesis is to fold. Obviously, the goal of my thesis was twofold. So the two was recognized as a too short word. Maybe it was pronounced too shortly. I don't know. And the outputs, the output by our English to Czech machine translation system from this input was something like, and the goal of my theory instead of thesis. So there was like a mistranslation of the thesis and theory. And this twofold was translated as is to fall apart. So instead of the goal of my thesis to be twofold, the goal of my theory was to fall apart. That obviously doesn't make any sense. And we see that recovering from this twofold is much easier than recovering from this to fall apart. The final user of the machine translation output has no other information to consider. So for the machine translation of the spoken language, there is a very large context needed, many sentences around. And if someone would be like giving a speech to you and you were following that speech through this speech translation system, if the person was all the time saying yes, we will close the deal, we will do it, and then suddenly in the final sentence he would say, let's forget it, or you're an idiot and I don't want to work with you. That very likely this isolated sentence would be an error of the machine translation system or the combination of the systems. So you would obviously lose some of your confidence in that deal, but still the majority of sentences that you have received so far would be like positive and approving. So when using these systems, you should the end user should rely on much more much larger context to get the full message correctly, because errors are going to be much more severe than the errors in machine translation alone or speech recognition alone. So let's look at the integration of these two components, and the core of the problems of the integration is the link between the sequence of words without any punctuation and lowercase and the individual correct sentences that are expected by the machine translation output. And there are a number of things that you can do here. The thing that we are doing now is we're introducing the segmentation step, a special component which inserts the punctuation, and then we feed the sentences to the machine translation system. You could also change the ASR to predict the correct punctuation directly, and that would be a better setup than we have now, because the ASR still has access to the full sound, so it could make use of pauses and of intonation and other like extra other non-verbal aspects of the input. And the fully end-to-end spoken language translation obviously somehow implicitly handles this segmentation. But the truth is that the current SLT system end-to-end are always trained and tested on data sets which already come in isolated utterances. So once you will see that yes, end-to-end spoken language translation is solved, you should bear in mind that it will be solved at the level of utterances. So if someone will be then listening and clicking mouse button after every completed sentence, then that particular utterance-based SLT system would work. If you still have to identify where the utterances are, the errors will be much greater, much larger than the SLT system alone would suggest. So about the segmentation, if we have a sequence of words, how do we insert punctuations? So the early models use simply language model scoring. So you were considering a window of a few words, and you were checking whether the probability of this sequence of words is higher or lower if the words are there without any punctuation symbol, or if you insert a comma, or if you insert a full stop, or if you insert a question mark. And you were quickly comparing these probabilities, and you were choosing the most probable one. Another approach would be to use sequence labeling algorithms. So you have a stream of words, a sequence of words, and for every word you are adding a tag, as in part of speech tagging. And this tag does not indicate the part of speech, but instead this tag indicates what punctuation should be used after this word. So maybe nothing, maybe a full stop, maybe a comma, maybe a question mark, and a capitalization for the next word, and other things. And there are many techniques, like underlying approaches possible. You can use it in Markov models, conditional random fields, or some recurrent neural networks such as LSTMs to do this sequence labeling task. And you can also consider this task a machine translation task. So in a spoken language translation system, you can easily have two machine translation systems running, one for the translation itself, and this one as a prerequisite, as a first step, a monolingual translation, translating from sequence of English words without punctuation to a sequence of English words with punctuation. And you can again use all the approaches that we have discussed, the phrase-based empty or some neural empty. In these setups that I've discussed so far, I have not mentioned whether we are using the sound information at all or not. If you go for the machine translation, then probably there is you wouldn't find an easy neural empty system that would have that would expect the sound there, so that could be a more complicated, especially in phrase-based empty, there wouldn't be any chance to include the sound. In sequence labeling, again, depends on the architecture. Sometimes it may be easier to feed in the original sound, and sometimes it would be difficult. And in the language model-based approach, there is no way to include the sound. But the sound is very informative. If I make a pause, it can indicate the end of the sentence. Actually, usually it does not correlate with the end of the sentence. But if I change the intonation, that definitely makes an indication of the end of the sentence, and also other aspects of the prosody play a role. Yeah. So here is an example of what can happen if you misplace the punctuations. So what the speaker said was some words and then all too well. And the speaker was saying something like, this approach does not generalize all too well. So he used kind of filler words, this all too well, that is a phrase which ideally you would say in a simpler way. But in spontaneous speech, people often use filler words, and these filler words were then uttered, they were correctly recognized, and the problem was that the segmenter decided to put a full stop after that all too. So what came out of that was, this approach does not generalize all too, and that was shipped to translation, and then the next sentence was, well, so to somehow conclude that the whole talk. So here you see the disfluency, and also this well was simply misplaced in the output. And these errors are in some very severe, because the machine translation system will take these sentences as trustworthy, and it will use even these surrounding words which maybe should not have belonged to the sentence in the first place, but the empty system will use them, and it will shuffle them and put them even into some prominent position in the sentence. So a random shift of the punctuation mark can terribly damage the final output. Yeah. So let's move to the end-to-end spoken language translation, which should not have these problems. But remember, these systems are trained and tested on corpora which are utterance segmented by themselves. The benefits of this direct spoken language translation is that all the uncertainty or the ambiguity of speech recognition is left unresolved until later, until also the target language model can affect that, can have its say in the decisions what was probably uttered. And also, potentially there are fewer neural network parameters, so there are fewer weights to optimize, and it is actually harder to train these end-to-end systems because the source speech and the target text are representationally too far from each other. But if you succeed in that, then this transition could be achieved with like fewer computations, fewer computation steps. So the main drawback, and I've already hinted that, is the insufficient training data. We already have quite sizable corpora for speech recognition, that is speech and the correct transcript, and we have huge corpora for translation, so parallel texts. Obviously, we have even larger texts that are monolingual, but we have reasonably sized parallel texts. But what we don't have is speech in the source language and the text in the target language in sufficient amounts. So what people sometimes do is they synthesize some side of that. So either they take a speech corpus and machine translate it to a target language, or they take a parallel corpus and they speech synthesize the source side, and then they train on the synthesized voice. That's one drawback, that you don't have appropriate data for spoken language translation. Another drawback is the input sequences are much longer. So you are now working with time frames of sound instead of subword units. And that is computationally challenging. So you need to fit all that input into the GPU memory card, and that's difficult. The alignment problem is obviously much more complicated than when you have text input. As I've already said, people are not really considering that the input comes non-segmented. The input is often assumed to come segmented manually and correctly into utterances. So here is an overview picture of the more important approaches to the training. That's again from the survey that I mentioned at the beginning of my lecture. And the standard training would be to train the speech encoder and the text decoder on the speech to speech corpus or SLT corpus, but this suffers from the insufficient training data. So what you can do is you can pre-train, you can use additional data. You can pre-train only the speech recognition, where you have speech encoder trained to produce the golden transcript. So for this you would use maybe a larger speech corpus. And then you would pre-train the translation system, where the input is the text in the source language and the decoder is producing the target language. And again, you would pre-train this, and then you would reuse the speech encoder and the decoder from the translation phase and fine-tune it on the small SLT data set. So this is the pre-training that utilizes the additional data. You could also use the teacher-student or knowledge distillation approach. There you train the parallel, so the machine translation system that goes from text to target text, and you create additional data with the teacher approach, or you force the student to produce the same probability distributions at its end as the teacher has. So this is another way of transferring knowledge. And then something which is similar to what we've discussed last week is the multitask learning approach. There you have the speech encoder to digest the speech, and you are training it with two like following components. One decoder that goes directly to the target language, and one decoder that goes to the source language. And in this multitask learning, you are training it on triples of input, the sound, the source transcript, and the target setting. And then at runtime, this system will be capable of producing both the transcript of the source and the translation in the target language. So you can again pre-train some of these components, but it is a setting in which the system is forced when it's being trained to consider explicitly consider the target the source language transcript, and that helps with the alignment because it influences how the training goes by knowing what are the word level units in the source speech. So here is a proof of concept that was the first serious attempt for end-to-end spoken language translation by Berard from 2016, and this exactly used the synthetic corpus. So it was small. It was the BTEC corpus, the basic travel expressions corpus, and the corpus is normally French to English text only. And Berard and colleagues synthesized French speech with 7 voices, and these voices are corpus-based and concatenative approach, so they are very repetitive. The same word is uttered in exactly the same way in the whole corpus, which also makes the sounds easier to grasp for the architecture afterwards. And the end-to-end neural network that was trained on this halfway synthetic corpus was a deep LSTM encoder, then the standard attention, and the deep LSTM decoder that so at the beginning did not have the words or subword units, but instead it had the MFCCs, which is the standard representation of frequency frames of sound. So the results on this small corpus were not too far from the cascading approach, but again I have to remind you that the input was synthetic, so the LSTMs could have kind of learned to classify the word samples because the words were too similar across the whole corpus. The first truly end-to-end approach was in 2018 by the same the team, and they have a speech encoder which uses some feed-forward layers at the beginning, and then the convolution, because we have to first reduce the input length to some smaller number of like positions. What people use here also is pyramidal recurrent neural networks, which is like a standard deep recurrent network, except that the deeper layers are not run at every time step, but they are run only every 3 steps or every 5 steps, and that this deep recurrent networks then condense the time dimension of the input. So then the bidirectional LSTM is digesting this condensed input of frequency time frames. Then there is the standard attention that we have discussed in the past, and they used character level decoding in this 2018 experiments. So they are predicting either the English transcription or the French translation, so they are using both sides of the data. and they train it in the multitask, they train it in multiple ways, but this is the pre-training approach. So they first train only the speech recognition, that is the dotted curve here. So the lower the better. It is over the learning steps, it is learning to produce the source side transcript. And then they switch over to the multilingual setting, where the system is suddenly expected to produce the target language transcript. And similarly for machine translation, they first pre-train it in the monolingual task, and then they add the source language. So the components of the neural network are pre-trained on like independent and easier to obtain data sets. Here are the scores. So the cascaded approach still delivers better scores, but if they put together all the end-to-end approaches they work with, then they are getting very close to that to the cascade. So the ensemble that gets the test blind score 15.5 compared to 15.8 of the cascaded approach is actually an ensembling system. So at every word, all the three subsystems help to decide. One of them is the directly trained end-to-end. One of them is pre-trained with the individual parts, with the speech recognition and the machine translation. And they also have the multitask training system. So the multitask alone performed best, but the best result is when they use these three systems at the same time. And I've mentioned that this joint pipeline can benefit from fewer parameters, and that is reflected in the last column. It's 9 million parameters that are used in this ensembling system, compared to 6.3 in the ASR only, and 15 or 16 million in the translation component. But remember, last week we have discussed the multilingual models, and there we were getting to billions of parameters. So to get a decent performance on open domains, you would definitely need to go much higher in terms of the size of the model. So here is a summary of the results from the survey by Silvachak, and we see that there has been quite a big improvement over the last 2 years, and we are really getting on par or very close to the cascaded system. What is still not clear is which architecture would be the best. So some people use convolution networks and LSTMs, some use convolution networks and transformers, some use pyramidal recurrent neural networks, some use the knowledge distillation, so teacher-student approach, some use pre-training, some use multitask setup. So it's a battle which is still running very fiercely, and we don't know which approach will win. The transformer alone can be also used in this approach. So this is a 2019 paper from the Italian FBK team, and they so this in the standard transformer that we have discussed in the past, you have the encoder which contains the self-attention layers and the feed forward network, and the input to this deep like 6-layered encoder is the combination of word embeddings and the positional encoding, because the self-attention is position agnostic, and they have modified that architecture in 2 ways. In one way, they have added these, similar to the Berard experiments, they have added the linear transformations, 2 layers of the transformation on the same combined input. Now the representation of the frequencies for the particular time frame and the position encoding, and then they used 2 levels of convolution network to reduce the size of the input, and then on top of that they put the standard encoder layers of the transformer. So this is like the baseline transformer approach, and they have a better setup, the S transformer, which uses similar compression of the input, the convolution networks, and some attention over that. And that is applied to the time frames still without the positional encoding, and the positional encoding is added to that output only right before entering the self-attention phase. So this is just an illustration that there are many possible components, how to put the network structure together, and all these different components will either help or damage your training capabilities, and this is a very recent research, so a number of experiments still will have to be done so that we will find the best approach. And I wanted also to mention another interesting example of now directly speech-to-speech translation. This is a paper by Google, and they they directly train a system to convert the spectrograms, the time frames of frequencies, into spectrograms in the target language, and they then use something which is called a vocoder that's actually synthesizing the waveform in the target language. The resulting system is called Translatotron, and well, as I said, I don't know anything about the target side, the speech synthesis, and I know somewhat about the ASR system, but the interesting setup here is that they also separate speaker characteristics. So after processing the spoken language on the source side, and after synthesizing or creating the sequence of phonemes in the target language, they concatenate this phoneme representation with the speaker information, and then they create the spectrograms in like a second decoder in the pipeline. And that allows them to preserve speaker characteristics in the speech translation. So you will hear the same voice, but it will be saying words in the other language. And the words do not appear as words in the representation. So the intermediate transcripts in the source and target language are necessary in the training phase. So they use them as auxiliary tasks in multitask training, but they do not use them in the runtime and inference anymore. So it operates like with full ambiguity at the level of phonemes, and you can from the system you can hear words which are not words, but the system they only are close to some words. So it is truly end to end. And it has the capacity of preserving the voice characteristics and also all the nonverbal aspects of that speech. And it's still somewhat worse than the combination of the spoken language translation and text-to-speech. So let me now talk a little about the presentation, but I'll only gloss over that. The presentation now in the speech-to-text translation is a critical thing because it can kill the whole show. So if you are showing your outputs too quickly, no one will be able to read it, and people will not get the message even if your translations were perfect. If you are updating your translation candidates, if there is like significant reordering in the updates, then you are again going to lose the person. They will not be able to reread it. And if you are deploying this system, you really need to make sure that it is deployed in a good setting. So maybe if the subtitles are too small and they would be perfect with perfect timing, still people would not be able to read them. So there is a lot of usability things that you have to consider. This is what we are trying now in our project, Eliter, as I mentioned. We are producing subtitles in many languages at once. And if you want to show these many languages to the multilingual audience, then you have very limited space for each of the languages. And with this limited space, it is often difficult to squeeze in the information and to keep it stable. So maybe a better option is to show paragraphs where people can read back, and with these paragraphs you can also easily indicate which sentences have been completed and which sentences are still being updated and which sentences are just incoming. So here you give a mix of like stable and unstable outputs, and the user can select what they would like to read. This is just an illustration of what we're struggling with. We have the ASR output, which is the sequence of words, and then we have the segmenter, and the segmenter inserts punctuation, and we are shipping these partial segments to machine translation, and then the segmenter will maybe decide after some more words arrive to put the punctuation at a different place. And then the machine translation will translate the complete sentences, and we are showing these concatenated sentences in 1 or 2 lines of subtitles. And the component that we had to develop for this, which we call subtitler, it decides when to move the subtitles 1 more line. And so that the user will see the subtitles not flickering, and what will be very annoying if suddenly something which has been already shown and moved out of the subtitle space of the 2 lines, if that would have to be updated because the segmenter changed its mind, and then the subsequent machine translation system changed its mind as well. So this illustrates that if you have a limited space, then you may be forced to emit some output and update it afterwards, and that will confuse the user. So there is also the cognitive load considerations. If the users are following some slides and these subtitles because they cannot understand the spoken language, then these have to be very close to each other, and they have to be like the same distance from the audience, because your eyes will need to accommodate if you would be looking at the slides on the wall and reading the subtitles on your cell phone. So that would not be possible to follow. So we had some test session with 2 Indian colleagues at our department, and they were able to follow a Czech talk through our system when they were fully focused on reading the subtitles instead of like looking anywhere else. And whenever they looked up at the slides, they lost track and they lost some content. I think I'm pretty sure that the settings, the paragraph view or the subtitle view that you have seen on the slides will serve better different types of users. So if the user understands the source language a little, then they can follow the source language, and they can look at the subtitles as in their mother tongue as kind of hinting or auxiliary service. And in that case, they will definitely prefer simultaneity over the precision and stability of the output, because they will be mainly following the sound, and the subtitles can hint them maybe some words they would not understand, they will appear there correctly. But if the user does not speak the source language at all, then we can give up on simultaneity because there is nothing that needs to be delivered as quickly as possible. So the user who doesn't speak the source language at all will prefer stability and precision over the immediateness of the translation, and these users will be happy to wait for seconds of delay. So that's why the 2 different views can be better for different settings. So this is again to illustrate that the task is very complex, and it has to be handled and considered end to end, because different set of users will probably prefer different final outputs, and these different final outputs then backwards will indicate that some of the underlying components are better or worse for the task. Yeah. I'm going to skip the evaluation of spoken language translation. I just want to highlight that there are more aspects to consider when comparing the outputs of machine translation system, text-based only. There you only consider the quality of the translation, and that alone is a complex enough task. But in spoken language translation, you also want to know how much are you behind what has been just uttered in the online setup, and some flicker, so how much of text is useless. So you are producing some intermediate outputs and you are showing them to the user, and if the user is reading them, you are wasting the efforts of the user if you are going to update those. So the flicker should be kept low, the lag should be kept low, and the quality should be as high as possible. This evaluation goes against the there is again the problem with segmentation. So you have some golden segmentation into sentences, but your systems may decide to segment the input sound differently, and in the evaluation you need to handle this mismatch in some way. So let's now move for the last part of the lecture to visual information, and this will be much shorter presentation. But here's the motivation. So if you have an English sentence such as a tennis player is getting ready, then the output could be tenista se připravuje or tenistka se připravuje. The difference may seem very subtle because you don't speak Czech, maybe. The difference is not so subtle if you know Czech. The first sentence is male, and the second sentence is in the female or feminine gender. And this information is not available in the English source, so you're bound to make random guess if you do not have additional cue. And if you have the cue, if there is an image next to that sentence, then you can easily disambiguate. Here is another example. So there is, again, a number of data sets, and please have a look at the survey that I mentioned. Another data set which is not in that survey is what we created. There is this database called Visual Genome, and that links images, rectangular areas in those images with English captions, and we have translated these English captions into Hindi. And the idea is to use the rectangular information or the whole image to improve the translation. And here's an example where even with the picture we didn't get it right. Two lamps lying in the sun was translated as some Hindi text, and the glosses, two baby sheep are telling lies. So lying was mistranslated. So here the picture maybe not maybe not helping as much as you would like to. Maybe they are lying in the sun and lying to each other. Both could be happening, and the picture doesn't indicate it. But still, lying in the sun is like more commonly the act of or related to the act of lying, and you could see that in the picture. So the picture could hint to the correct translations. What we did is we created a dedicated test set or challenge test set that was focused on ambiguous words. So we have searched the whole visual genome. It's automatic Hindi translation, and in about 3 million strings of like this description of small regions in the image. We found actually very few words that would be ambiguous. Maybe that's the side effect of using machine translation system, which did not have rich enough vocabulary in the target language. So there were only too few ambiguities arising. But then we manually subselected, and we arrived at 19 words that are ambiguous on their own. The first one could be stand or cord. This is how often they now appear in the challenge test set. And these words have different translations. So one of these words which was not there, we were trying to find it in the corpus, but it just didn't appear in the whole visual genome. And a word ambiguous like that could be mouse, which could be translated as the rodent mouse, or the computer mouse. And there would be different Hindi words for that. So mouse would be another ambiguous word, but it didn't appear in the data set. And then the point was to translate sentences with these words, and hopefully the image would have helped. Here is an example of the word penalty. And unfortunately, as you see, obviously the images indicate that the penalty in the left-hand picture is the fine that you will have to pay for something, and the penalty or the penalty box is related to the soccer game in the right-hand picture. So the pictures here are clearly informative. But the problem is that the words around in the input sentences are already sufficiently informative. If you have a street sign advising of penalty, it would not be in a soccer game. And if you have a penalty box and the white lining around it, that again will indicate that very likely this is related to soccer game and not to paying a fine. So the surrounding words can be very informative. Yep. So here is an example so here is a reminder how the visual information can be used. Before I describe how the visual information can be used, let me remind you of the attention architecture that we discussed very early in the series of these lectures. You have the input sentence, you process it with bidirectional recurrent neural network, and then you attend to these states that correspond to different words in the sentence, and then you are producing the output, and this attention mechanism will always focus on another part of the input sentence as you proceed and produce the output. This attention mechanism was used in the past not only for input sentences, but also for input images in the image captioning task. So here you have an image encoder. Here the images are processed with convolution networks to reduce down the dimensionality. And the image has like a 2D representation, the annotation vectors for the regions in the image. And you run the attention mechanism not over this one-dimensional sequence of input tokens, but you run it over the two-dimensional parts of the sentence. And you use the same decoder afterwards. So this image captioning task has no source language. It has only the image, and it's producing the expected output of the description of that image. And it attends to the various parts of the image as it's producing the output. And if you put these two setups together, then you will have the multi-encoder setup. You simply attend to either the source words or the parts of the source image, and then you have one decoder that produces the output words. And this is exactly the same type of combination that we had with multiple text inputs in the multilingual lecture last week. So this is one possible setup, how to use the image information with an additional encoder of the image. This is a picture, an illustration from a paper of colleagues of mine, Jindřich Libovický and Helzel, and they combine these two attentions, the attention over the source text and attention over the image in multiple ways. And the particular setup that was working best for them was called the hierarchical attention. So the hierarchical attention is illustrated here. Here the output of the system is ein Mann schläft auf einem grünen Sofa in einem grünen Raum. And the input sentence was a man sleeping in a green room on a couch. And this is the hierarchical attention. So in the first line, we see how often or how to what extent was the decoder looking at the source words. The second line says, to what extent was it considering the image? And it's all black, so it's very rarely considering the image. And the third step is how often it is considering itself in self-attention, so looking at its previous output words. And we are now focused on the on the visual information in this setup. And I said that the line 2 is all black. It's actually not fully black. There are lighter spots when we are talking or when the decoder is producing the word greenen. So when the color is mentioned, the color of the room is like very clearly green on the slides. So this green color was so salient and so informative that the decoder took a little look at the visual information. So with this setup, you can see how often the visual information is actually used in the system. And there were a number of shared tasks in this visually supported translation run. This is the summary table again from the survey by Sulubachak, and you see that people use various approaches. The hierarchical attention is among the best ones. What people also use is like parallel attention, so running these two attentions and not combining them directly. People also use imagination, and that's another multitask setup. There the encoder is processing the input text, and it is trained with the objective to produce the target text and produce the target image representation. So it is like thinking what the image could be. So you need the data set which has, for the training, which has the input text, the image, and the output text, but you are using the input image not for the encoder, but rather for the decoder, and the decoder is imagining what the image could be. And this imagination is also a successful strategy. So that's another paper there. But still, in most cases, the plain text translation was performing better. And Desmond Elliott has made an interesting experiment. He has in our experiments, when we were using this English to Hindi translation, the challenge words that I was talking about, the penalty box, these words were translated perfectly, even with a system that did not look at the images at all. Desmond Elliott's experiment is even more directed at this exploration. So what he used was several multimodal systems. They were trained to consider the image, and along with the input sentence, such as 2 dogs play with an orange toy in a tall grass, he fed the model either with the correct image, which is 2 dogs in the grass, or with a random wrong image. And this non-congruent image was pretended to help to be useful for the input sentence. And interestingly, only the hierarchical attention approach was sensitive to that image. So the other setups in which people use the images work equally well if you provided them with the correct image as if you provided them with the wrong image. And that means that the image information was never used by those models. So the hierarchical model was the only one which really learned when to observe the image, and it got a worse performance when the image was non-matching with the input text. There are other papers where the images have not helped much, so that's mentioned there as well. This last paper from Ozan Kaglan is trying to document that it's not a problem of the methods, that they do not use the visual information, but it is the problem of the data set, that the data set does not need the visual information to carry out the task. So what they were doing, or actually that was Desmond Elliott's paper, sorry. So what they were doing is that they were degrading the text input, and they were removing all the words and replacing them with just a void placeholder for words whose meaning, the meaning of which could be recovered from the image. So we have this tennis player, and the original sentence was a young girl in white dress holding a tennis racket. That was the original sentence. So the original sentence was already clearly stating that this was a female. So in my motivating example, I have replaced that with the gender ambiguous term tennis player, but the original sentence in the data set actually mentioned the gender. And therefore, in the original setting, if you were given this this sentence with the gender mentioned, the translation would be perfect, and it was perfect, and you would not need to look at the picture at all. In the Desmond-Elliott experiment, they removed the gender-specific word, and they left there only a young someone in something holding a tennis something. So they've removed the colors, and they've removed the other words that could be guessed from the image. And then with this degraded input, there was indeed a difference between the systems trained on text-only information and systems trained on text and visual information. So the NMT, the non-multimodal setup, produced a boy, so guessed that on average it's boys in the pictures, and the color was also blue instead of white, and the image-informed system actually picked up this information from the image, and it correctly produced a femme, the French word for girl, and the French word for the correct white color. And here similarly, the color of the towel was hidden in the source text, and the multimodal system was able to pick it up from the image. So the final message is that the architectures really are capable of finding the relevant information, at least concerning colors and some key other aspects such as the gender. They are able to pick it up from the image, but mostly this information is not needed, and the text, as we normally write it, will already contain the sufficient information. So with that, I would like to finish the lecture. We were discussing speech translation for a long part of that. We were first putting together the ASR and machine translation systems directly. Each of them independently are maybe superhuman, but when you put them together, you will realize that they are not quite fit for that, because one is producing words only and the other expects sentences. The segmentation is a difficult task. Because, by the way, people do not speak in sentences. They often interrupt themselves in the middle of a sentence, and it's difficult to decide what would be the best unit to translate. So that's why people look at the end-to-end approaches, where all the uncertainty would be gracefully like passed over towards the end of the pipeline, and that in the target language, the language model could still consider that and like choose what is more appropriate in the context. But it's only very recently when these end-to-end architectures are getting towards the performance of the cascaded ones. And I've also mentioned a number of practical problems when deploying this subtitling, including the presentation issues. And then I've talked about translation with visual features. So the motivation is that the image can provide the missing context to resolve the ambiguity, but maybe the image is not always needed. So to fully summarize this, I would say that a picture is worth 1,000 of words, but only in 1 of 1,000 of cases. So that's it. That was the last lecture on machine translation, and you have seen the evolution of the systems. You have seen the previous state of the art of phrase-based MT, and finally we got to machine translation surpassing humans in certain areas, and we also indicated today how machine translation can consider other modalities, other relevant information that could help to disambiguate and produce better outputs. So thanks for watching, and remember to look at the slides which are on the seminar webpage, and I'm looking forward to some other opportunity to discuss further developments in the area. Thank you.